Hi, in this video we're going to be discussing our CG2271 Tutorial 2. Okay, so this tutorial was basically to recap on the interrupt principles that we covered in class. Okay, again, this is also related to the lab for that you would have just recently completed. Okay, on the interrupts with the switch and the LEDs. Okay, so the first question uh, is a basic question regarding how we are able to relate interrupt numbers with their actual sources. So here we are given three interrupts: IRQ 0, 10 and 31, and we are asked to find out where does it relate to. I mean which peripheral devices do these three interrupts map to. Where can we get the information? So as I mentioned before, one of the main things for this module that I also want to emphasize is the need and the habit of trying to find your information in the right places. And almost all the times you can always get your answer from the data sheet. okay uh, in some cases you may also be able to get the answer from the software development environment that you're using, because of all the header files that have all the definitions that you need. So we're going to explore both of these right now. So if I were to look back at my um, uh, PDF file, the data sheet, where can I go? So since this is related to the interrupt, so I can go and do a search. So for example, I can do a search for the NVIC, which is the interrupt vector table, the interrupt vector controller. And that is in page 51 over here. So if I were to scroll down here, you can see the information relating to all the interrupts that are here. So as mentioned in class, the vector from 0 to 15 are internal to the ARM processor. So you cannot sort of override them in any way. And from 16 onwards are the non-core vectors. That means these are related to the interrupts from all the peripheral subsystems within the microcontroller. So the interrupt IRQ0 in this case is mapped. So you come back here in 0, 10 and 31. So 0 is mapped to DMA channel 0, 10 is mapped to SPI 0, and 31 in this case is mapped to port D. So that is using the data sheet of the microcontroller to find the information. And as I mentioned, you can also find the information from the software development environment. So if you open up your project uh, files, you will see that there's one file that you always get compiled together with your code. It's called the mkl25z4.h. That's the header file that contains all the necessary declarations and definitions for the registers within the controller. So at the top there, you can also see the enumeration that has been declared for us, and the same numbers are also used here. So DMA is number 0, SPI 0 is number 10, and 31 is port DIRQ. So I've shown you two sources where you can get this information from. And just make it a habit that whatever you want, always try to go back to the data sheet or go back to the software environment and try to get the information from there. In most cases you will be able to get the information that you need. So that sort of gives us this first step of information to relate IRQ numbers with the appropriate peripheral devices that are tied to those interrupts. Now the second question is about interrupt priority. So in this case we want interrupts to be serviced in this particular order: 10, 0 and 31. So that means this is the highest priority. So if you remember our priority numbers, they are basically 0, 1, 2 and 3. And this being the highest, and this being the lowest. 0 is the highest and 3 is the lowest. So I can set it as, for example, 0, 1 and 2, or 1, 2 and 3, or 0, 2 and 3, doesn't matter. It will still behave in a similar way, just looking at these three interrupts. Because IRQ 10 is the highest priority, followed by 0, followed by 31. Okay, in terms of priority, okay, there are actually 8 interrupt priority registers, IPR 0 to IPR 7, which we covered in the lecture. Okay, and you can see that out of these 8 registers, each register is handling the priority for 4 interrupts. Okay, so 8 into 4, 32. So it covers all the 32 peripheral interrupts that the system handles. Okay, another interesting thing you will also notice is for each, though we have a 32-bit register, each of it is 32 bits, we only use 2 bits out of 8 bits for each interrupt. Okay, and why don't we use all 8 bits, okay, or all 32 bits in each register, and then we only need to use fewer registers? Yes, that is a possibility. uh, so one of the reasons, okay, that the manufacturers do this, which I also mentioned in the lecture, is that sometimes they have plans. Okay, they have plans for uh, expanding the functionality of these registers. Okay, so they intentionally reserve some bits, okay, for future expansion. Okay, so what is it used for? Maybe right now we do not know, but in a future release of this controller, an upgraded version, maybe these bits will now be used for other settings associated with the priority or some other functionality. Okay, so it's intentionally done, okay, by the manufacturer to plan for future expansion. Okay, so for now we just focus on the bits for the priority, and the way in which we can do it is basically by setting or by using these functions called the NVIC set priority. Okay, and these 3 library functions basically help us to set the priority according to what we want. So we only need to provide these numbers 0, 1, 2, and 3. Okay, and what they will do is they will shift the bits accordingly. So if I were to set the priority as 1, okay, that translates to a binary value of 0, 1. And what will it do is 8-bit value, but this 0, 1, which is actually here, will be shifted to the left by 6 bits, so it will come here. Okay, so that relates to a value of 64. Okay, similarly, if it was 10, it will be 128 and so on. Okay, and if you really want to see what is happening, you can always go back to our code, okay, and actually look at what the library function is doing. Okay, so that's what I'm going to show you now. Okay, so if you open up your code base, okay, and if you right click, okay, on this set priority, and you go to this definition of set priority, okay, it will bring you to its internal definition, and from there you can go to its actual definition, and there you can see the code. Okay, so what you can see is happening is it is actually taking the priority that we provide and it's shifting left. Okay, and this is actually defined as 2. Okay, this is defined as 2. So 8 minus 2 is 6. Okay, so it's shifting left by 6 bits, okay, and doing some masking operation, okay, and then setting it to the appropriate register. Okay, so this code is sort of giving you the idea of what is happening, but since we already have the NVIC set priority library function, we can straight away use it. Okay, but if at all you're interested, okay, to know what is actually happening at the back end, you can always dig deeper, okay, in the code to see what is actually happening. Okay, so that is how the set priority function actually works, okay, by manipulating, okay, the information in the appropriate IPR register. Okay, so as I mentioned before in the announcement, we do not need to worry or memorize all these actual registers. Okay, we are not going to do that. As long as we know how to use the library functions, that is what is important. Okay. Okay, the part B to this question is basically enabling and disabling the IRQ, or enabling and disabling IRQ. So there are 2 registers involved. One is the ISER, okay, and the other is ICER, okay, interrupt set enable register or interrupt clear enable register. Okay, interestingly, you need to set a 1 to either set it, okay, and at the same time you also need to set a 1 if I don't want to uh, clear it. That means I do not want the interrupt. I want to disable the interrupt. Okay, and basically why it works this way is because there are 2 separate registers. Usually if it is a shared register, okay, then a 1 would be setting and a 0 would be disabling, but these are 2 separate registers, ISER and ICER, and for both of these registers, the way it works is I must write a 1 to sort of enable this function. So for the ISER, if I write a 1 to that particular bit, I am enabling the interrupt. For the ICER, if I write a 1 to the particular bit, I am disabling the interrupt. Okay, so again, this is another sort of behavior you will see in some controllers, where writing a 1 is actually to disable some functionality. Okay, so it's not always 1 is enabled, 0 is disabled. In some cases, it could be a 1 to enable and at the same time 1 to disable as well. Okay, so you need to sort of read the information in the data sheet or the handouts quite clearly to understand how to use these registers. Okay, now so of course in our case we have these library functions nvic enable and nvic disable to help us with this. Okay, so now let's go on to question 3 and 4. Okay, question 3 and 4 are very similar. Okay, and basically what we are trying to do is we are trying to analyze this behavior of a main loop. Okay, a code with a main loop, and you have an interrupt that is occurring at a particular rate, and you want to be able to analyze and see how the dynamics, okay, changes, okay, as the interrupt frequency changes or the amount of time in the ISR changes. Okay, so the first information is that we have a 48 megahertz device. Okay, so we have a KL25Z. Okay, it's running at 25 megahertz. Okay, so the crystal is 25 megahertz. Sorry, not 25, 48 megahertz. Okay, so at 48 megahertz is running, and we have an interrupt that is being triggered. Okay, an interrupt that is being triggered at every 10 kilohertz. Okay, at every 10 kilohertz interval. Okay, and every time you trigger the interrupt, you need to jump to the ISR, and the ISR itself, okay, is given as taking 14.9 plus 1, okay, microsecond for the total execution as well as the overheads, okay, in the context switching. Okay, now given this information, first thing is what percentage of the processor's time is spent servicing the interrupts, including the overheads. Okay, so since the interrupt frequency is 10 kilohertz, we know that the period is 100 microsecond. That means every 100 microsecond. Okay, so if I look at it as a timing, okay, if this is t equals to 0, okay, every 100 microseconds, t equals to 100 microseconds, there is an interrupt. Okay, then 200 microsecond, there's another interrupt, and so on. So every 100 microsecond, there's an interrupt, and every time there's an interrupt, I need to jump to the ISR, and inside the ISR, I will consume a total of 15.9 microsecond, including the overheads for the context switching. Okay, so the total amount of time that I spent servicing interrupts is 15.9 seconds out of 100 microseconds. Okay, because every 100 microseconds, this event occurs. Okay, so every 100 microseconds, this event occurs, and every time it occurs, I use 15.9 microseconds of time. Okay, so the percentage of time servicing interrupts is 15.9%. Okay, now the next thing is what percentage of processor's time is left for the main loop. Okay, so since 15.9% of the time, okay, so every time I spend a bit of time here with the ISR, I spend a bit of time here with the ISR. Okay, so how much percentage of time is left? Okay, so with the main loop, okay, for the main loop to execute. So every time I have the interrupt, I use up some time. So the amount of time that is left is whatever is remaining. Okay, so it's 100 minus 15.9, which gives me 84.1%. Okay. In part C, you're basically told that the main loop requires 37 milliseconds of computational time, okay, to execute one iteration. What is the minimum main loop update rate? Okay, so if the how do you go about analyzing this question? So the first thing is we need to understand the amount of clock cycles you have, okay, available once you come out of the besides the interrupt. Okay, so we know that we are running at 48 megahertz. Okay, so this is the total amount of cycles we have every second. Okay, and since we only have 84.1% of time for the main loop, that translates to 40,368 thousand cycles, okay, that is left. Okay, and one clock cycle takes 20.83 nanoseconds, okay, 1 over 48 meg. And since the main loop requires 37 milliseconds, okay, 37 milliseconds divided by 20.83 gives me 1776000. That is the total number of cycles I take for one iteration. Okay, that means inside the main loop, okay, I have something. Okay, so for example, you have a while one loop. Okay, so I do this and I go back, I do this and I go back. Okay, and of course in between there will be interrupts. Okay, there will be interrupts. Okay, and one iteration of this takes me 37 millisecond. Okay, and that relates to 177 uh yeah 1776,000 clock cycles. Okay, now what is the percentage of cycles in the main loop? Okay, so since the main loop has this amount of time, okay, that is allocated to it, okay, how many times can I do it? Okay, so the percentage of cycles in the main loop is actually given by this number of cycles for one iteration divided by the total number of cycles that you have, okay, for the main loop, okay, which is given by this 0.043995, and that is the in terms of the actual percentage of cycles. Okay, so the frequency is the reciprocal of it, which is 22.73 hertz. Okay, so basically what we are trying to do here is we are trying to find out, okay, totally what is the percentage of cycles, clock cycles you have inside this main loop over here. Okay, so inside this main loop here. Okay, so that is what we are trying to find out. Okay, how many times or how frequently can I run this main loop, given that I have that an interrupt that is also being triggered, okay, at a particular rate and consuming a certain amount of CPU time. Okay, so that is part C. Okay, for the last question, question 4, basically is exactly the same thing. Okay, the exact same thing. Basically, only thing difference is your interrupt is running at 25 kilohertz with your interrupt taking 34 plus 1. Okay, so previously you were running at 10 kilohertz. Okay, so previously your interrupt was at 10 kilohertz and taking 14.9 plus 1. Here you're running at a higher rate, 25 kilohertz, and taking more time. Okay, inside the ISR with overheads. So if you look at the answers here, you can see that even without calculating, you will know that definitely you're going to have more time spent on the ISR and lesser time spent for the main loop. Okay, so if you look at the amount of time spent on interrupts, you have 87.5% of time spent on the interrupts and only 12.5% for the main loop. Okay, so if the main loop takes 37 milliseconds of computation time to execute one iteration, okay, the update rate, okay, if you do the same calculations, you will see that it really comes down to 3.38 hertz. Okay, so you can see that, okay, if I were to just do a comparison, you have a 10 kilohertz with 15.9 microsecond, okay, and the other one was 25 kilohertz with 35 microsecond. Okay, so these are the two different scenarios here. Okay, and the frequency of update, okay, for this is 3.38 hertz. Okay, whereas previously it was 22.73 hertz. Okay, so you can see very much, okay, that very clearly that just with one interrupt, alone, changing the frequency of the interrupt and changing the amount of time that you spend in the ISR has a very, very significant effect, okay, on how frequently you can run the main loop. Okay, and just imagine that right now, if in the main loop, okay, instead of the current list of tasks, I add in some more, and this one has to go a bit longer. Okay, so I need more time in the main loop. Okay, there could be a period of time where I'm really not able to fulfill any of the timing requirements within the main loop, okay, at all, because the interrupts are happening so frequently. Okay, so this sort of gives you the idea and the motivation as to why this approach of using a main loop and interrupts, though it works for us, okay, it has worked well for us, okay, in many projects, okay, it is definitely very limiting, okay, because it is not scalable. Okay, the moment your interrupt dynamics changes or your number of tasks you need to do in your main loop changes. Okay, so this is something very important. Okay, and that is sort of the motivation that we have as we move towards the multi-threaded environment. Okay, where we know that even if the project is scaled up, more interrupts, okay, the way you design the architecture can still allow you to fulfill all your timing requirements without compromising anything. Okay, so that is the motivation. So this question sort of gives you uh, a clear uh, rationale, okay, as to why we are moving in the direction towards an OS. Okay, why an OS is important? Because as you can see, okay, with the current setup, okay, with the current timings that we have, uh, a small change in the interrupts dynamics, okay, or even adding one more interrupt will really change the entire dynamics of the whole system. Okay, so I hope that is the key takeaway that you get. Okay, so that sort of wraps up our tutorials discussion. Like I said, if you have any questions, okay, please feel free to clarify with me, or you can also post in the forum, okay, and I will also answer from there. Okay, so that's about it. Thank you. I will see you for the next tutorial. Thank you.